Let's dive right into a question that sounds like it's straight out of science fiction. If our reality is basically a massive computation, can we take a tiny piece of its source code and run it on one of our own quantum computers? Well, today we're going to see how we can go from a wild theoretical blueprint of the cosmos right down to hard data from a real quantum chip. So, here's the plan. We're going to start with the big idea, the cosmic blueprint laid out by a theory called observer patch holography, or OPH. Then we'll look at the fundamental building blocks of that reality. The really cool part? We'll see how those blocks leave a unique, testable fingerprint. From there, we'll jump into how that was tested on IBM's quantum cloud, look at the jaw-dropping results, and try to figure out what it all means.
All right, let's start at the very beginning with the core question that OPH even tries to answer. Now, this isn't just some late-night philosophical question, right? OPH treats this like a serious engineering problem. It puts you in the shoes of a single observer and asks, if everything you see is just information, what would the actual hardware, the nuts and bolts of the machine you're living in, have to look like? Okay, so what are the parts of this cosmic computer? Let's zoom in and look at the blueprint for the microphysics of the system itself. So, at the most fundamental level, the proposed hardware is a network, kind of like a geodesic dome, on the surface of a sphere. All the information is stored in tiny quantum registers that live on the connections of this network. But here's the crucial part. At every intersection, there are strict local rules that force the information in neighboring registers to be consistent with each other. Everything has to fit together perfectly, like a puzzle. Okay, and this is where it gets really interesting, because there's a huge translation step that has to happen. You see, the theory describes reality using qubits. Think of a qubit like a dimmer switch. It can be in many different states at once. But our quantum computers, they're built from qubits, which are more like simple on-off light switches. So, to test the theory, you first have to figure out how to program your simple on-off switches to perfectly mimic the theory's complex dimmer switches. And this isn't just guesswork. There's a very clear step-by-step recipe. You have to figure out which logical states are even allowed by the OPH blueprint. Then map those onto specific combinations of your physical qubits. After that, you build all the operations and checks using the basic programming tools a real quantum computer gives you. This whole process is what turns an abstract idea into an actual program you can run. So you've got this beautiful theory, this elegant blueprint. But how in the world could you possibly test it? It's not like you can just open up the source code of the universe. Well, the key is that this very specific architecture, with its specific rules, leaves a unique mathematical fingerprint on the quantum states it allows. And this formula, the heat kernel law, is the smoking gun. This is OPH's big, testable prediction. It's a very precise claim. It basically says, if you look at a tiny patch of this system, the chances of finding it in any of its allowed states aren't random at all. Nope, they have to follow this exact mathematical curve, which is determined by the state's properties. It's a very specific, totally non-obvious pattern to go looking for. With such a sharp, falsifiable prediction in hand, it's finally time to go to the lab. And what's so amazing is that in our time, the lab can be IBM's public quantum cloud, something anyone can access.
So here's the game plan they followed. First, you don't try to simulate the whole universe. You just pick one tiny, simple system where OPH makes a really clean prediction. Then you do that quadit-to-quadit translation we just talked about. Next, you fire up a real IBM quantum computer, prepare that state, and measure it, thousands and thousands of times. From all those measurement shots, you piece together the probabilities. And then comes the final, simple step. Do the results from the hardware show the fingerprint that the theory predicted? And this is the moment of truth. What actually happens when you hit run? Do the patterns you measure on real, noisy, imperfect quantum hardware actually match this pristine mathematical idea from the OPH blueprint? For the very first test, which was based on a simple 5-step symmetry, the theory's complex fingerprint boiled down to a single incredible number, the golden ratio squared. That's about 2.618. I mean, think about how specific that is. It's not an approximation, it's an exact target, popping right out of the theory's geometry. And just look at this. It's stunning. The target was 2.6180. The ratio they actually measured on the quantum computer was 2.5974. That's a difference of only 0.8%. For a real-world quantum device, that is an unbelievably precise match. The fingerprint was there. But, a good scientist is always a bit skeptical. A single success could just be a coincidence, right? A fluke. The real test is if the predictions hold up when you try something different, something more complicated.
So the next step was to test a different kind of symmetry, one where the order you do things matters. Like putting on your socks and then your shoes is very different from doing it the other way around. So for this more complex case, OPH predicts a completely different fingerprint. This time, the ratio of probabilities should be a beautiful, clean integer, exactly 2. Another sharp, unforgiving target with no wiggle room. And this tells such a great story about how science actually works. The first run was off. It came back at 1.87, which is a 6.4% error. Kind of disappointing. But instead of giving up, they dug deeper. They realized the specific physical layout of the qubits on the chip was creating a bias. So they cleverly reversed the layout to cancel it out and ran the test again. The result? 2.0299, just 1.5% off the target. The prediction held up. It was there all along. So let's take a breath. What do these incredibly specific microscopic tests actually tell us? We've shown that these tiny, abstract patterns predicted by a theory of reality's fundamental code can actually be built on our own little silicon chips. This quote from the source document just says it perfectly. No one is claiming that the IBM chip is a tiny universe. Instead, the chip is being used as a test bed. It's a way to check if the mathematical structures that OPH says should exist at the very bottom level of reality are just mathematical fantasies, or if they're things that can be physically created. And really, that's the bottom line here. We've managed to go from a hugely abstract theory about the microphysics of the universe all the way to concrete experimental evidence. It's forged a link between a proposed model for reality's source code and real-world measurements that we can do right here and right now. And that just leaves us with this provocative, almost dizzying thought. If these tiny systems that we build and measure really do reflect the fundamental blueprint of the cosmos, well, that opens up an entirely new way to do physics. We might have just found a way to experimentally poke at the nature of reality itself, one qubit at a time. So the only question is, what should we ask it next?